Today, me and my dad are going to conduct the photoelectric effect demonstration for my 5th grade science experiment.
Well, what is the photoelectric effect? Well, the photoelectric effect is the process by which you shine light on the surface of a metal and that emits electrons from the surface. This process was first discovered in the late 19th century by German physicist Heinrich Hertz, and he found that the intensity of the light did not matter unless a certain threshold wavelength was met. So in other words, the wavelength of the light had to be below a certain level, which we call the threshold, in order for the process to occur. If the wavelength was above that level, regardless of the intensity, the photoelectric effect did not occur. However, once you get below that threshold wavelength, then the intensity does factor in to how many electrons are emitted from that metal. Of course, this baffled physicists at the time because classical physics could not explain this effect. So, fast forward several years, and famous physicist Albert Einstein wrote a paper on this, and he came up with a novel explanation for the photoelectric effect. He didn't discover it, of course. He came up with an explanation for it. And what he did is he borrowed from Max Planck's quantum theory ideas that were just published a few years before that, and he showed that Planck's quantum theory could explain the photoelectric effect. And for this effort, Albert Einstein won the Nobel Prize in Physics. So, I guess now we should move forward with the experiment. So, what materials do we need for this?
Materials that we need for this. First, we're going to need a PVC pipe or a plastic rod. We're also going to need like a wool sweater of some sort. It doesn't have to be wool, but something like that. We're also going to need the gold leaf electroscope. And we're going to need a metal to put on, which we have right here.
Yes. And what we're going to use for our experiment today is zinc. Okay? Zinc, of course, conducts electricity. And one thing you'll find out about the photoelectric effect is that the threshold wavelength is unique to each metal. So for zinc, the threshold wavelength is roughly 310 nanometers. A nanometer is 10 to the negative 9th meters. So it's really small. For other metals like sodium, the threshold is in the visible light spectrum. It's roughly about 520 nanometers. Of course, the visible light spectrum runs from about 400 nanometers to roughly 700, 750 nanometers. So today we're going to use zinc, and we have a nice zinc disc here. So at this point here, I guess we'll just start the demo. And as my son said, you don't really need too much for this. So the first thing we're going to do is use some steel wool to rub the zinc disc here. And the reason we do that is to remove a thin oxide layer that forms on most metals once they're exposed to the air. You can't even see this oxide layer, but that interferes with the experiment. So I'm going to rub this several times on both sides. And then I will put it on top of my gold leaf electroscope. Now, one thing you'll see about the gold leaf electroscope, of course, is that there's a leaf here, a very thin leaf, and right now there is no charge applied to this. And what will happen is, when my son here charges it, you'll see the gold leaf move. So,
in order to charge it, just take the plastic tube and rub it with the wool. Hover over the zinc, or whatever metal you're using. Touch in the metal of the zinc and roll off to the left. And as you can see, we should have a nice charge. You can see that the gold leaf moved, and what the electroscope does is it measures the angle. So what happens is when you apply the negative charge to the metal, it repels the gold leaf, and right now it's at an angle of about, roughly 30 degrees. It's tough for me to see from this angle. So there's a negative electrical charge applied to this. So, now remember, electrons are negatively charged. So, with the photoelectric effect, what will happen is we will shine a light source on here of different wavelengths, and if we meet the threshold wavelength, you'll find
that the charge, it discharges. So in other words, we move electrons from the surface, and that will cause the gold leaf to move back down to 0. So, as I mentioned earlier, the gold leaf, or the zinc, has a threshold of roughly 310 nanometers. I'm going to use a UV lamp here, and this UV lamp runs at 2 different wavelengths. It has a short wavelength of 254 nanometers, which of course is below the threshold, and it also has a wavelength of 365 nanometers, which is above the threshold. So we're going to turn this on. First, we're going to show the effect. So we're going to run at the 254 nanometers threshold, or 254 nanometers, and we should produce the effect. So,
and so as you can see, it's turning on.
It's turning on, and you will see.
And you need the UV light has to be lower for the from the nanometers that this threshold is. If it's not lower, then it won't move the gold leaf at all.
It doesn't really matter how intense, how close we hold the lamp, it will not happen. So here we will show it.
This is below, so it should happen. It should move now.
So we will hold it over the top of the metal here, and you should see the gold leaf move. Okay? There you go. See? So, let's just fully discharge this. Okay. It is fully discharged. Let's charge it again and show them that even if we have it at a very low intensity, as long as the threshold is met, we will still discharge the electrons. So we'll charge it one more time, and we will run at a wavelength lower than the threshold. So let's see, do we have a charge? Oh yes, we got a nice electrical charge here.
About 40.
So once again, I'm running at 254 nanometers, which is below the threshold, so this should produce a photoelectric effect even if the intensity is low. So even if I hold it fairly high, you will see the gold leaf move. You see that? Which shows us that the electrons are discharging from the surface of the metal, which is removing the negative charge. Let's see, are we back down to? We are down to 0. There we go.
And the intensity differs because obviously if someone holds a flashlight far away from you, it's not going to hurt your eyes at all. But if someone shines a flashlight right at your eyes, you'll definitely see it. And that's how we measure the intensity. If you hold it higher, less intensity. Hold it closer, more intensity.
Okay. Well, an important part of the experiment, let's make sure it's fully discharged. An important part of the experiment is actually to show that that the effect does not happen if the wavelength is above the threshold. So go ahead and charge it. So do we have a charge? Okay. Now I'm going to turn it on the long wavelength, which is 365 nanometers. Now 365 nanometers, of course, is above the threshold. So we should not see any discharge on our electroscope, regardless of the intensity, because this is above the threshold. So I've got to get my UV lamp to warm up. See, there's my UV lamp. One thing, just a note of safety here, do not shine a UV lamp in your eyes or anybody else's eyes,
will blind
because it could damage you.
You will be blinded.
So we are now going to hold this above our zinc disc. This is at 365 nanometers and high intensity. I'm going to put it just above.
It should not work at all. It should not
and you'll see that even though I'm holding it very, very close,
it does not go down.
There is no discharge. Okay, I'm just holding it there a little bit longer just to make sure you know that I'm not playing with the time here. And there's no discharge on our leaf.
I mean, if you hold it super close, sometimes the wind from it will knock it a little bit, but it'll always just go back to the stump.
Exactly. There's a little movement, just like you said, because of the draft.
But it goes
But the gold
back,
leaf has not discharged. so we are not emitting any electrons from the surface of the zinc. So that is really the nature of the experiment. I'm going to just discharge the, you know what, just to show the effect again, we still have the charge on there.
We have a large charge, it's at 90.
Is it? What? Oh my God, we have a really big charge on there now. I'm going to discharge it here once again using the low wavelength, 254 nanometers, which is below the threshold. So even though I hold it high, is it moving?
We never discharged it, and that is a crucial part of the experiment.
Oh, there we go. Good thing my partner told me we didn't discharge it.
That means that it'll have a positive charge, and if anything, it'll move it up.
Okay, so we want to discharge it, and sometimes this is a real bear to discharge here. Let me just, there we go. I just had to touch it. Oh, one thing is when you're running this experiment, wear latex gloves, and the reason for that is that you don't want to get your oily fingerprints on the surface of the metal, because that could interfere with the photoelectric effect. So there we go. So let's just charge it again. We'll just run the demo one more time.
And I'll show how to do it from this angle. Just touch it in the middle and roll it off on the left. And you should have a nice
There we got the discharge.
It's at 60 right now. And it's turning on the UV lamp.
I'll turn on my UV lamp here. Now, remember, you know, as we stated multiple times here, you know, the threshold wavelength matters. Just remember, also in physics, is the lower the wavelength of the light, the higher the energy. The higher the energy, exactly. So what happens is low wavelength light has higher energy, and that higher energy knocks the electrons off.
So we're at the 254 nanometers
So
here.
let's see. So I'm going to hold it. Even though this is low intensity,
it is still moving, as you can see. Moving slowly but surely.
It's moving slower than with high intensity, but it's moving.
And now it has touched.
It's fully discharged? Is it fully discharged? All right.
Yes, it is.
There we go. One other machine that we use for this, can we back it up, because we don't need to focus on this anymore here. One other machine that we use for our experiment is a multi-wavelength LED light, okay? And what this has is, this has light in the visible spectrum, roughly from 380 nanometers to 624 nanometers, and we have about 8 settings here. And we use this for the sodium effect, because sodium actually has a threshold wavelength that's in the visible spectrum. It's about 520 or so. So we did use this for sodium. However, all of these wavelengths are above the thresholds for the other metals that we did. And what were some of the other metals that we did?
We did aluminum, we did silicon, and the other one was magnesium.
Magnesium.
And sodium is a highly reactive metal, so
Yes.
if you ever use that, be careful with it.
Definitely, and you are totally right there. The sodium is rather difficult to work with. It's super reactive, and it oxidizes immediately upon exposure to the atmosphere, so we could only do a couple runs with that one.
So,
and also sodium is quite dangerous to work with, so I would recommend great caution when working with sodium.
So here we can adjust the nanometers.
There we go.
Here and here, we can also adjust the intensity.
Intensity, exactly. Also, special thanks goes to the Johns Hopkins Physics Laboratory for loaning us both the LED lamp and also the UV lamp. Without that, we couldn't run this experiment, so we definitely appreciate their assistance. So I think that's it. Is there anything else we should mention?
Well, here it adjusts the intensity. Here it adjusts the nanometers. So if we turn up the intensity to low intensity and we move these nanometers, it can change. So at the start, 380 nanometers, you have UV light. Here we have a little bit brighter UV light, and then here we have violet light.
Violet, yeah.
After that, we have blue light, and the next one will be green light, and the next one will be a little bit darker green.
Okay, and that's at about 525 nanometers. And you see how the colors change as we move up the spectrum.
If you move it again, you get like a yellowish light of some sort. Then move it again, you get the orange light. And of course this is going up in nanometers, not down. So these are not gonna work on many metals.
Yes, yes. And actually most of the metals have pretty low thresholds in the UV spectrum.
And move it the last time, you get a red light. And the red light shouldn't work on almost any. Because the sodium has one of the highest thresholds. So these
are lights that did work for us. And you can see these are in the visible
a couple
spectrum.
did, but like the red didn't and the orange didn't.
Okay. So that's it. Well, thank you very much for joining us, and I hope you learned something today about the photoelectric effect.